Hello and welcome again to my Physics Online video lecture series. Today's video is a follow-up to another video that I made in which I discussed pulleys and strings. In today's video I wanted to not really introduce anything new, but sort of work some examples from that previous video. So this is sort of like a supplement to the other video. We've already discussed tension, how tension works, in some sense what the process is for solving problems with tension, with or without pulleys being involved. So today I just wanted to work an example or two to discuss this further, to sort of like show how the process works. So what I have here is an example in which you have a pair of masses that are connected via an ideal string, and the right mass is pulled to the right with some known force. And what we want to know is what the acceleration of the two masses is, as well as how much tension is present in the string. So the basic process for solving this, there's kind of two ways you can go about it, and they both amount to the same thing. You should be drawing a free body diagram for each of the two masses. So let's say that this one is mass A, and in the picture you can see that mass A is sitting on the table. It has some coefficient of kinetic friction. So we know that there is going to be a force of friction resisting its motion. We know that there is going to be a normal force from the table. We know that there is going to be some gravity on this mass, and then we also know that tension is going to be pulling the mass to the right. If you were to set up the Newton's laws for this system, you'd basically end up with, for mass A, force of tension minus force of friction is equal to mass A times acceleration. And you could further that by essentially saying that the force of tension is equal to mass A times acceleration plus this friction force, which should be the normal force, which we established earlier was, it's a flat table, so is equal to the weight. So mass A times G times the coefficient mu kinetic friction. Okay, for mass B, if we draw the same free body diagram, what we have is a pulling force, so we could label that as F pull. We again have a normal force. We again have a gravity force, so FGB, which should be MB times G. And then we have tension as well as friction, force of friction on B. So if we set up the set of forces for B, what you end up with is pulling force minus tension minus friction for B is equal to MB times the acceleration. And so we could essentially, with some rearranging, we could say something like F tension here is equal to the pulling force minus the friction, so mu k mb times A, minus mb times A, it should be times G, minus mb times A. Now notice that I have isolated here the tension force on the left-hand side of both equations. So I should be able to just set the right-hand sides equal to each other. And so what that leaves me is that the pulling force minus the coefficient of friction times mass of B times G times mass B times A is equal to mass A times A plus mass A times G times the mu. So I guess maybe we'll put the mu before the masses just for consistency here, mu k. All right, we're trying to solve for acceleration, so we want to isolate that on one side of the equation. That gives us mass of A plus mass of B times acceleration. That is basically adding this term to both sides, and then we have to subtract this term from both sides, and we'll put this side, which is on the right here, on the left ultimately. So this looks like force pull minus the mu k times mass B, or mass A, plus mass B times g. Okay, so now we can actually solve for the acceleration. The acceleration should look like, basically divide both sides by mass A over mass B. So by doing that, you have that the acceleration is the pull force minus the coefficient of friction times the sum of the two masses times g, all divided by the sum of the two masses. So now we're ready to plug numbers in. So your acceleration, coming back over here and looking at the numbers that we have to work with, this right here was mass A, this is mass B, this is that pull force, this is mu k. So what we have is 12.5 newtons of pull force minus 0.045 coefficient of friction times, and then it was 3 and it was 2, so times 2 kilograms plus 3 kilograms times 9.8 newtons per kilogram, which is the g factor, all divided by 2 kilograms plus 3 kilograms. And so when you plug all that into a calculator, you get 1.959 meters per second squared. If you're rounding to two significant figures, then this might be rounded to 2.0 meters per second squared. So that is our answer for the acceleration. Now we just have to do for the tension. And to do that, we just basically grab either one of these equations. I'm going to take this one. So force of tension should be ma times A. Remember that ma was the 3 kilogram mass. So we have 3.0 kilograms times, and we can use this whole number if we'd like, 1.959 meters per second squared. And then from to that we must add ma, which was again 3 kilograms, times g, which is 9.8 newtons per kilogram, times that coefficient of friction 0.045. And so when you do all of that, you can put it into the calculator to get. And by wonderful choice in numbers, you end up with 7.2 newtons. And that is actually the number you get out of your calculator if you retained all the digits up here. Okay, so that's that example. You could then double check by going back and plugging in the acceleration that you got and the force of tension you got into this other equation and making sure that the two sides are equal. I won't do that in today's video though. Let's do our other example. So you have two masses that are connected by a string running over a pulley. The tabletop this time is frictionless. We want to get the tension in this string and the acceleration of mass m1. So again, we can draw our free body diagrams. Mass m1 is the mass that's on the table. Basically, it just has a friction force, a tension force pulling to the right. It has a normal force pulling upward. It has gravity pulling downward. So that would be m1 times g. If we were to do the sum of forces on it for mass 1, what we would get is sum of forces is basically the tension force plus gravity on one plus normal force on 1, and again these two will cancel, and that has to be mass 1 times acceleration, and the result is that the force of tension must be m1a. Now we repeat this process for mass number 2. Mass number 2 had a tension force acting upward on it. It has gravity pulling downward on it. So we could call this Fg2 or m2 times g. If we do the sum of forces on mass number 2, what we end up getting is just Fg2 plus Ft is equal to m2a. And so by putting signs in, taking downward to be positive in this case, what we end up getting is m2 times g minus Ft is equal to m2a. Now to solve this system of equations, basically we'll make use of this equation and this equation, and we're just going to substitute the Ft from this equation into the Ft for this equation. So what that ends up giving us is that m2g minus Ft, but that is just m1a, so minus m1a is equal to m2a. So m2a. And that means that m2g is m1a plus m2a. And so in turn that means that that the acceleration a is equal to m2 over m1 plus m2 times g. This side right here could be rearranged as m1 plus m2 times a for what it's worth. Okay, so that we come back over here, we have to look up what each of these masses was. m2 is 2.5, m1 was 5.5, both in kilograms, so we have 2.5 kilograms divided by 2.5 kilograms plus 5.5 kilograms. And then that is times 9.8 meters per second squared. Throwing that into a calculator, we get 3.0625 meters per second squared. So retaining the two significant figures that we should maybe retain here, we would say this is about 3.1 meters per second squared. Okay, now we can go back to our equation that says Ft is m1a. So that means that Ft is 5.5 kilograms. Remember that 5.5 kilograms was mass m1. And then the acceleration we just solved for above, 3.0625 meters per second squared. So if we put all that into our calculator, what we end up getting is 16.84375 newtons. Rounding to two significant figures, we end up with 17 newtons. So we would say 17 newtons here at two significant figures. All right, so that was two nice examples for this idea of tension and pulleys and how they operate and how they work with each other. Hopefully these examples have clarified or helped you to understand better the other video that they're attached to. Hopefully you understand this topic a little bit better and have learned something from watching, and thanks for watching.